Okay, good morning, everyone. Well, my name is Gabriel, and I work at CI&T. CI&T is a Brazilian company, which actually is a multinational company, focused in software delivery, digital transformation, lean digital transformation, and we have a special group there called Cognitive Studios. I'm also a PhD student at ITA, the Brazilian Aeronáutica Institute of Technology. And basically, I want to talk with you about the latest research advances in recommender systems, especially using deep neural networks. Okay, so I hope you can apply in your work and generalize these principles to other problems that are somehow similar. Well, Chris Anderson, in the well-known book, The Long Tail, said that we are leaving the information age and entering the recommendation age. So now, instead of just segmenting our customers, uh, with the digital transformation, the customers are empoderated. They want to be special. They want a personalized service. And companies are treating not then just as cluster or segments, but as millions of ones. So we are now in the personalization age. And we all know, maybe this is the most popular machine learning application for the broad audience because everyone uses news portals, use e-commerce portals like Amazon, services, entertainment services like Netflix, and streaming like Pandora and Spotify. So we all know that the power that personalization brings for the user's engagement. And of course, companies are looking to earn more, to increase their profits and their fidelity and reduce churns by means of recommender systems. Here is a general picture of the main approaches of recommender systems or main techniques. We will not be able here to drill down in each of these topics, but the main family of recommender systems approach is collaborative filtering, which means that you take the user's behavior and use them to find either users similar to you with similar behavior. And in this example, after identifying similar users, they can recommend you items that these similar users like it and probably you like. You have approaches based on user similarity, based on item similarity, but the main point of collaborative filtering is that it ignores totally the items metadata. And by items, we are talking here in a news portal, the items are news. In Netflix are series or movies, okay? They ignore all metadata. They just uses user behavior to guess what's the best recommended items for you. Another important family is content-based filtering. It does not use, it may use some interaction, but it uses also metadata of the items. So for example, if you saw a movie of a specific actor or director, you may be interested in other movies of the same director or actors, just in a simple example. So they leverage metadata from attributes and users to recommend, okay? And there are the hybrid approaches that try to combine both metadata and user interactions to provide the best recommendations. Talking about collaborative filtering, we have the memory-based techniques that are based on similarity, like nearest neighbors, and there are the model-based techniques that are based on machine learning models. And the most prominent one is matrix factorization. Most recommended systems we use in our daily basis are based on this technique. It was devised during a large competition that took place in 2008, sponsored by Netflix. And the main objective is that as input you have a matrix like this, and you have a set of users as rows and a set of columns as items. And it's a very sparse matrix, which means that for each user of the whole repository of items, think in Amazon, think how many items or products they are there. Maybe you have bought a few of them. So just for these positions, you will have a value attribute that by 1 and zeros in the most positions. So they are very sparse. And the objective is which other items you have not bought can I recommend? So this is a mathematical model that factors this matrix R in two matrices. one of users and one focusing on in the items. And you can define the number of the features you have for each user and for each item. They must match. And then the objective is that once you've learned these two matrix, when you multiply, then you will reconstruct this matrix with some errors, okay? You wanna minimize those errors in the predictions of whether the user has bought or not our product. And when these errors are minimized, you can take the other predictions for items you have not bought or viewed or interacted and get a recommendation from them. So it's a very scalable. If you want to try in Spark, there is an implementation of ALS, matrix factorization, using implicit feedback, and it scales in a Spark cluster. So you may want to take a look. But this is traditional approach. Let's talk here. The objective here is to talk about the recent research about recommender systems using deep learning. Some of them are already in production by major tech companies like Google, like Pinterest, etc. But most of them is at research time and may be productive in the industry in a few years. Okay, so now let's go a little deeper and talk about why deep learning for recommender systems. Deep learning is all about learning a representation, okay, using a set of layers and nonlinear transformations so that you can learn hierarchical set of features. And this somehow matches the objective of recommender systems. For example, you may use feature extractions directly from unstructured data, like images, text, audio. Using deep learning, you can extract those features and use them as metadata for the items. That brings information to the model. You also may mix heterogeneous data, so you can generate an embedding of an image, combine it with some categorical features, some numerical features, scale them up properly so that the neural network can learn, and it just works using multimodal data. Dynamic behavior with RNNs. So RNNs are great for sequence modeling. And if you think in user sessions, they are a sequence of events, and you want to predict what's the next event. So they match perfectly with this objective. They can learn more accurate representation learning generally than the matrix factorization because it has more information, especially item metadatas. And RecSys is a complex domain, and deep learning has worked well in other complex domains like image classification, object detection, so at least it worth a try in the domain of recommender systems. Here's a brief perspective of how deep learning has been used in the research of RecSys. So there was a seminal paper in 2017 using deep Boltzmann machine for rating prediction, and they showed it could improve a little bit state-of-art matrix factorization at that time. Then there was a calm before the storm, and then in 2015 there was a few seminal papers on this area, especially on the usage of RNNs to model session-based recommendations. And then in 26 it starts the boom. So if you look at the main RecSys conference that is known as ACM RecSys, you will see that a large part of the latest papers are trying to explore the usage of deep learning to improve recommendations. The first deep learning recommender system workshop was in 2016. I had the opportunity to be there, to have been there, and saw the earliest papers about this theme. And then the interest continues to increase in the last editions. There are lots of papers, but I think we can summarize these approaches in these four main approaches using deep learning for RecSys. The first one is deep collaborative filtering, that is, user interactions to produce embeddings of users and items and recommend. Learning item embeddings specifically. Feature extraction from the content, especially unstructured data. And session-based recommendations with RNNs and their combinations. So most papers are exploring these combinations of those approaches. I talk briefly about some of them and deep dive in two cases in the end of the presentation. So what's an item embedding? An embedding, as you know, is a vectorial representation of an item, generally a categorical item. So you think in the items of recommender systems like news or movies, you wanna get a numeric representation, a vector of that represents that movie, so that you can compute easily similarities and recommend the items to users. You wanna that similar entities embedding are similar. So if Star Wars 4 and 5 are similar movies, you want their representation, their vectors, to be similar also, so that the system can work. They usually are used to initialize items representation and also use it in item-to-item recommendations. So it's a key block in any recommender system using deep neural networks. Here's an interesting example. It was from a paper from Yahoo on 2015, product to vec, that mimics the idea of words to vec. Okay, so in words to vec, it's an algorithm from deep NLP. The main idea is you define a window size, and you slide over your words of your text, and you have two approaches: skip-gram and SIBO. Here is a skip-gram approach, that is, given a word, predict the words that are in the same context, assuming they are similar, they are semantically related. So the sky is blue. So you can take blue and predict whether sky is in the context, right? So the same idea has been applied for recommendations. If you imagine a basket in e-commerce as a sequence of products you have added, you may try to predict whether I have, let's say, a specific product in this basket. What's the probability of having other products in this basket? So this way you can learn a projection or embedding, a representation for this item in which similar items have a similar embedding, okay? So it's the idea of algorithm from deep NLP applied to recommendations. Talking about a little bit about feature extraction, right? We have lots of unstructured data. We have images, like it may be an image from a news portal talking about a store. Maybe there's a hypothesis that this image may add additional knowledge about this content, right? This is a hypothesis. Maybe for Pinterest, for example, where the main content is the image, it's worth to extract the embedding of the features of this image, and you can use pre-trained networks like Inception for that, and you get a representation of that image and embed it into a neural network. Talking about text, we have RANs, we have CNNs with one dimension. So in RANs, you are considering the order of the words. When you're using a CNN, you generally define a window size, and you extract the most relevant features from the text. And then you transform a text with variable length into a fixed length representation that you can use in your neural network. And the same for audio. RNNs and CNNs are being used Spotify uses it to detect your preference based on which style of music you have heard. Maybe you do not know about music theory or rhythm or tones, but your pattern reveals that you like some kind of music, and this approach can infer that and use it to recommend unknown users for music for you that you might like. And how do you combine those information together in a hybrid system? User interactions, and item metadata. Generally, there are three main approaches. You may use item metadata embeddings that you learned previously to initialize items representation. You may use a regularization approach, which is you may use item interactions to produce an embedding, use the item metadata as the other embedding, and try to maximize the similarity between those. So if they are very different, they may be used as a regularizing term in your loss function. Or you may join. You may just concatenate, let's say, as an example, in Pinterest, you have an image. You may use the image embedding, and they are fixed, they are not training over time. And then you devise an embedding for to capture the interactions of the users, and you let this part of the embedding to be trainable. So you learn a mixed representation for this item to a specific user. If you want to try a single model, a starter model of deep learning for recommender systems, I would recommend the wide and deep learning approach. It was published by Google in the deep learning workshop. And it's easy to use because Google has made it available easily as a candidate estimator in TensorFlow. So you can easily plug your features, see the results, and run it in a scalable fashion in Google ML engine. So you can quickly see the performance of your model. How does that work? Basically, it combines a wide model, which is, a wide model that's basically a linear model, like logistic regression, okay, with a deep model, and they are trained together. So the error in your prediction, the backpropagation, is performed on both networks. So when I heard about this, I thought it was just a great idea, because according to them, the deep neural network focuses in generalizing, and the linear model focuses in memorization. What does it mean, memorization? Let's say you are building a platform for advertisement, and you want to capture the relationships between the publisher of the advertisement and the website where the ad is being displayed. So let's say it's an advertisement about a Nike tennis, and you expect that maybe in a ESPN website, there will be more conversions of this tennis than in other, let's say, a Vogue or a fashion portal, right? Because of the audience of that website. So when we are using linear models, generally you combine features, you make feature interaction, so that for categorical features you can have a feature that says, if the ad is about tennis and it's in the ESPN website, the conversion will be this. So it kind of memorizes what it sees, whilst the deep neural network focuses in generalization. So I thought it was a great idea. They reported that their offline results for this model for apps recommendation was kind of about the same in offline evaluation, but when they used the A/B test to evaluate, they observed an increase over simply the wide model. So I decided to give it a try and test in a very large data set. So I chose the data set of this competition in Kaggle, the outbreak click prediction. The objective was, given a set of ads that were shown to the user, rank them so that the ad that user actually clicked is in the first position. So it uses a ranking metric. It was huge because it had 2 billion page views and 70 million click records and more than 500 sites. This was a real Kaggle competition. I participated from that competition and was in the 19th position in the end, using simple techniques like linear logistic regression, factorization machines, that's not so simple, and then with a simple ensembling layer on top of that. And I was anxious to see whether the wide and deep model could improve the results, maybe make it less required to do some ensemble and some crazy feature engineering. So I give it a try. This was the database, okay? It's structured database. So what you get? This is the trained data set. You have the display. That's the session of the user, that display of the page. The ad, and for each ad shown in the page, you have a label that is clicked on or not, that you want to predict. Obviously, for test sets, you don't have the information of which ad was clicked. And then you have some metadata about the document. You have some categories, entities mentioned in this document. They refer to articles, so you have textual information there. And also you have information about the user visit, like timestamp, geolocation, etc. Okay? So you have item information, you have user information about his context, and these features are of different types. You have numerical features like scalars, you have temporal features, spatial features, categorical features, and the first step is to think, how do you prepare those features to input into the model? And TensorFlow, in its higher TF layers implementation API, it makes it easy to combine, to wire all those features together. So they provide a candidate estimator that is called DNN linear combined classifier, which is the wide and deep model. And you provide the set of linear features, okay, the set of deep features or features prepared for deep neural networks. For example, you don't want to use item embeddings for linear models, but for neural networks. So you need to make some transformation. They are the same features, the same raw features, but they are transformed in a different way according to the model. And you define some other settings here, okay? Here is an example of how we wire together the wide columns. So for the linear model, we use one-hot encoding for categories, and there are categories here with more than 6,000 different values. So it leads to a very, very sparse vector for each row of your data set. But there are frames that work really well with those sparse representation. Whilst in deep columns, for features with low cardinality, you can use one-hot encoding, and with higher cardinality, you use embeddings, okay? So it will learn an embedding, a vector, for each different advertisement, for each different document published, etc., for each categorical value. And then the results. Here in the first line are one of the models I used in the competition. It was Walpole-Wabbit. It was a linear model that makes it easy to make feature interaction and hashing to reduce the number of the features. And the result in this competition metric that was mean average precision, it measures the quality of the ranking. So if from the 6 ads I put in the first position, they actually click the item, I get total score. In the second position, a lower score for that row. This was a score of my best model with Walpole-Wabbit. And then, after doing all this effort, I could put into work the TensorFlow model. And the linear model on TensorFlow was a little bit better than the previous I could get with Walpole-Wabbit. I think the Walpole-Wabbit model took, it ran just in a single server in about 12 hours, and using TensorFlow ML engine, a simple cluster could have that done in 6 hours of training. I have a deep model also that was trained in about 12 hours. And then the surprise, the deep model was much lower, had a much lower accuracy than the linear model. Then I expected to see the results for wide and deep model, and I couldn't get the result I could have with linear model. So that teach me a lesson that there's well known that there's no free lunch, but I really expected that either a deep model or a wide and deep model could have could learn a better representation and have a better accuracy. So as Google report a short increase in the accuracy in offline evaluation, I could observe even worse here. Maybe providing this information to the user with A/B testing, we could have a real picture, but you must be careful when you are applying deep learning. You need to reduce your expectations, is the message here. Okay, so now we are going a little deeper. I will talk a little bit about my research. It's focused on news recommendation using deep learning for recommender systems. Okay. News recommendation have some different aspects than general recommender systems. You have a very sparse user profiling, which means that each time you enter in a website, if you have not enabled your cookies or if you are using different device, the news portal knows about anything about you. And you just read a few news articles from the huge data set they have. So they are very sparse. The larger publishers like Globo.com have publishes about 1,000 news a day, so it's very dynamic and fast growing. The interest in the information decays very deeply. as time passes. So news from the past week doesn't matter about anything this week. And the user's preference also shifts. Now we are all interested in World Cup. Maybe not all of us are interested in football and soccer during continuously, right? So the user's shift change. So this was the research objective of my research. This is how a thesis objective look like. It's a hypothesis or a task in order to improve to achieve a result. So my objective was to investigate, design, and implement a deep learning meta architecture for news recommendation. And by meta, we mean that the architecture may be prepared to change so that I can change components and compare to improve the accuracy and satisfy information needs. Here is just a picture to show that there are many factors that influence the news relevance for a user. For example, the attributes of the news, like the publisher, the topics. There are dynamic properties also, like the recency of the article, how old is it, and its popularity. And you have also context information about the user. This chart shows here in the y-axis is the number of clicks, in the x-axis is the age of the article. So you see that the peak of the age of the article is when it's one day old. When it starts to get older, the interest in it starts to decrease up to after 3 days. Nobody cares about this new. So they have a very very high decay in the information value. So you need first to devise, when you are building a machine learning model, you also need, as in usual software development, devise what are the requirements of that model. Because if it does not scale or does not perform well, it will not meet the requirements. So the requirement was to work well in extreme code start scenarios when you don't know about anything about the user, to learn in news representation, use deep learning, to use user session information of the current session, and if it's available, use information from past sessions, to leverage users' context information like time for news. It's on a hypothesis that whether you are in a conference, where you are at home or at work, you may be interested in different content, and also times of the day also change your interests. So you need to take into account this context information. The dynamic properties of the news, like popularity and recency, we saw that they're important. And another important requirement was that it should have online learning. I would like to train in a sample just once, so that it scale. I don't want to stop each day and run a job with the increasing number of the user interactions and news published and train using past data. I'd like a model where each item is passed once and you have a streaming data being training this model. And finally, it should have a modular structure. So this is the big picture of the main contribution of my thesis. The left side is focused into learning item representation of the article. So I want to input text here, like New York is a multicultural city, and some metadata, and want to learn an embedding that will be used for recommendation. And the part in the right is focused in recommendations, actually. So in the left part, the objective was, given a text, what's the vectorial representation of it? Here we have a t-SNE visualization, where we see the colors are the categories of the items. So we see that this neural network, we use CNNs here in this first trial. We can separate in 2 dimensions by category. And you see that there are some here. I used a German news portal, and you have here some clustered information, news articles about Berlin and about sports. So once you have the pre-trained articles, here are the posts. They are in German. I don't know anything about German, but I know some keywords, and then they really talk about Super Bowl, NBA. They really talk about sports, I guess. So the similarities are high. Obviously, Google Translate was great for this evaluation also. And then in the second part, we work in the recommendation, actually. Okay? So what's the input of this model? You have a batch, a training batch, and the batch is for each line here, you have a user session, okay? So we have this user read 5 news in each session, this one, choose two articles and so on. So what you want to predict? You want to predict the next click of the user. So you take, you know that user has clicked in the first item and the label or expect output is the second item and so on. So I prepare batches this way and throw into a RNN and LSTM to work on those predictions. There's a step here of negative sampling. You cannot compare. Generally, in classification problem, you have a softmax in the end, and you have a fixed number of items. But as in this case, we are increasing constantly new items. You cannot do a softmax in the end. So we need to sample some negative items that the user has not clicked in the session. This is done this way. I take items from the same batch that the user did not click and use it then as negative samples. And in the end, this is the final loss function. Okay, instead of a softmax and cross entropy, what I want to maximize here is the similarity of this learned embedding, okay, with the actual clicked new of the user, actually read new from the user, and minimize the similarity with the negative samples. This way, I'm not limited. I can change the number of the items without changing my architecture and without having to retrain the whole data set. This formulation here can be made by a few lines of TensorFlow. They are the same. And in the end, I have a loss function, which tries to maximize the similarity of the predicted embedding and the actually clicked article embedding. Then comes the evaluation. The basic idea is to train. My protocol was to train up to this hour, the model, and then try to predict what will be the next clicks in the next hour for the sessions. So I use ranking metrics, recall 3, that verifies that within the sampled items, they are in the top 3, and NDCG takes the actual position into account. And then I benchmark with very, very popular algorithm, but with no machine learning here, that are commonly used in news portal, like within the most recent clicks, what was the most popular news is the popular recent. Co-occurrent is basically market basket. So for each item, for each article, which other articles are read together in the same session, and content-based, just similarity of the content. Then, after some weeks working in TensorFlow, I was like this guy, pretty excited about what would be the results. But after the results, I was like this. There's no case tool to transform your PowerPoint, your model into TensorFlow. It was a hard work, but the results were like this. So the blue line here is the model, okay? Here you have the recall metric. And you see that most of the time, the recall is a little better than here in the x-axis is the actual, I use it at the set with 30 days, okay? So here are the days. I expected a larger difference, but I could get just a small one in this first trial. Is another metric, NDCG. And here you can see better the distribution. Here is my model. It's 4% better than the baselines. That doesn't use machine learning at all. So let's go back to the model, rethink something, and I have some trials to do. But it's common in machine learning model that there are very hard baselines that you will strive to beat. But as you increase in the accuracy, it gets harder and harder to improve. Here's the blue line is my model. So here you have the 24 hours of the day. The hypothesis here was is that my model performs better in the morning, in the evening. You can see it performs a shortly better throughout the day or throughout the 30 days of training. Okay. So next steps in this research specifically for the ACR model is to try different word embeddings. I use pre-trained word2vec. On Wikipedia, I would try GloVe. Try different feature extractions like RNNs to extract features from text. And in the recommendations module, there are lots of things to do, like test different RNNs, different negative sampling techniques, leverage past sessions of the user to initialize for newer sessions, evaluate in larger data sets. We've worked in a partnership with Globo.com, and we will work in a 5-month data set, and it's huge. I'm anxious to see the results. And hypertunings, hyperparameter tunings. I will leave you with 2 main references. This one was a workshop of the author of the first paper of RNNs for sequences, for session-based. It's a very good material. I did not touch deep matrix factorization here, but here's a lab that was made by Mopatel in Strata conference. It's worth lots of sample codes, how to implement that. I also will leave you share with you a data set we've made available at CI&T for you. There are lots of user interactions and articles there. It's from an internal used platform, and there you can try on your. We have some kernels we've prepared as the first steps in recommender systems using Python. Okay, and that's it. The last notice is that we are hiring. We work with NLP, with computer vision. Here's a link you can apply, or you can just drop me a mail. We will be happy to talk with you. Thank you.